Okay, great. Let's start with the second talk then.
Thank you very much. So you're here, okay. So now I'm going to talk about the reverse picture of how previous talk was computational complexity trying to help algebraic combinatorics understand what it's doing. So this talk is going to be about how algebraic complexity can help computational complexity theory to understand what it's doing. And it's going to be we are going to now go to the algebraic complexity theory, so not the usual one where the classes P and NP are. So we're going to talk about the algebraic version of P versus NP, and these are the classes VP and VNP, and the V stands for Valiant, Leslie Valiant, who is actually here at Harvard. So what's the model? So this time we're going to be computing polynomials, formal polynomials in formal variables. And what are we allowed to do? We are allowed to put in arbitrary constants from some fields, and actually for the rest of my talk, this field F is going to be the complex numbers. So we have arbitrary constants, we have our formal variables. We input them in a circuit, and at every node here we are going to perform an elementary operation. So these are what's called the gates. And there is a flow, so this is a directed acyclic graph here, and there is going to be one sink, and in the sink we are going to get the resulting polynomial. So here in this example, so this is a circuit that computes this particular polynomial. And the question is, what's the smallest size of a circuit that we can use to do that, right? And by size, I mean, let's say, number of nodes. With or without the inputs, it's not going to matter in what I'm going to say. So there is going to be the class VP, which is variance P. So these are families of polynomials which can be computed with circuits with polynomially many nodes. And when I say polynomially many, I mean polynomial in both the number of variables, which is in this case n, and the degree of the polynomial. But for all practical applications, the degree of the polynomial is going to be, is not going to be large. It's going to be smaller than or equal to the number of variables. So we shouldn't worry about this. So what are some examples? Well, here is an example, the power sums. So we can do that. We can also do elementary symmetric functions, which is not that obvious how one can do a short circuit, because otherwise, as you can see here, there are too many. It's a big sum over monomials, but it's possible to compute it. In fact, it's depth 3 circuit. And then there is the class VNP, variance NP. So, and this actually very much resembles this Sharpie class that I talked about, is the class of polynomials which we can write as an exponential sum over polynomials, which themselves, so basically they are indexed somehow by this sequence B, but we can also put it as an input here, so it's 0, 1 entries. So exponentially many, sum of exponentially many evaluations of some polynomial, which is from VP. Okay, so the quintessential example is, so this class contains every explicit polynomial that you can actually write down, like the monomial symmetric functions here, where you can take all possible monomials with exponents alpha 1, alpha 2, and so on. As long as you can actually write down the coefficient here, you are going to have something in VNP. But it's not necessarily, so you can maybe use another basis where you can nicely write down your polynomial. But certainly, if you can actually write it explicitly in terms of in some easy presentation, then it's going to be in VNP. Okay, so what's the connection with P versus NP? So there is some connection. So if actually VP is equal to VNP over a finite field of constants F, or over C, and the general Riemann hypothesis happens to hold, then P is also going to be equal to NP. So what do we believe? We believe, of course, that VP is not equal to VNP. And so this is going to be the main conjecture we're going to work towards. Well, we're going to see how we could possibly try to prove this, that VP is not equal to VNP. Okay, so how do we do this? So thanks to the question before, so is everything a determinant? In some sense, the answer is yes. So what is the determinant? Of course, everybody knows. So here our variables are going to be the entries of this n by n matrix, so n squared many variables, the degree is n. So with this presentation here, this puts the determinant as a polynomial, formal polynomial, puts it in V and P. But it's actually, so if from linear algebra, of course, we know how to compute it much faster, compute a determinant, and actually we can do this with an n-cubed sized circuit. And so the determinant is in VP. And even if we don't allow division, because usually in row reduction we do some division, but you can do this without doing divisions, it's still going to be polynomial time. But so it's in VP, it's also universal. In other words, so if you take any function, or any polynomial which is computed, which can be computed by a formula of size S, so S many terms, and by what we mean by formula is something slightly more special than a circuit, but I'm not going to go into the fine differences here because it's not really going to matter for the big question. So there is going to be a matrix of size 2s by 2s, with the entries are either variables like single degree 1. So degree 1 basically polynomials or constants. So that the polynomial is equal to this determinant. And for every polynomial, of course, then there is going to be some minimal sized matrix which computes it. And this is going to be our determinantal complexity of the polynomial. And here is an example. So if we take this polynomial here, we can compute it as this 2 by 2 determinant, and in this case we can say that the determinantal complexity of the polynomial is 2, because we cannot do it with a 1 by 1 determinant for sure, because we have a degree restriction. But of course, so figuring out what is the minimal such matrix is going to be hard. Okay, so what Valiant showed is that if the determinantal complexity is polynomially sized in terms of the degree of n and the degree of the polynomial, that's equivalent to the polynomial being in VP. So in other words, we can use this determinantal complexity as a complexity measure of our polynomial, and depending on how large this number is, we can figure out if it's in this class or not. Okay, so now the next polynomial is the permanent, which is almost like the determinant, except it's missing the signs. And now there is no more linear algebra, and permanents are pretty nasty to compute. And so we can see this also because the permanent is VNP complete. So first of all, it is in VNP. Just from this presentation, basically, we can write it down in terms of these monomials. exponentially many monomials, and we can figure out its coefficients. But it is actually also VNP hard. So in other words, for every polynomial in this VNP, there is going to be a matrix of some size m by m. Again, where m is actually polynomially large in terms of n and the degree of the polynomial, such that, and the entries in the matrix are affine linear forms, such that the polynomial is going to be equal to the permanent of this matrix. So in fact, determinants are powerful. We can compute everything with it, but permanents are even more powerful. You can compute more. So basically, you can compute more polynomials with a smaller permanent in this case. But the problem is that the permanent is not nice. It's not an efficient thing to compute, and this is really what we want to prove. So basically, if we want to show that VP is not equal to VNP, that it means that the determinantal complexity of the permanent grows super polynomially in M. So it's bigger than any polynomial size. And we want to show that the permanent is basically not in VP, and that's going to be enough. So this is the main conjecture now. So we compare determinant versus permanent and try to find the determinantal complexity and show that it is super polynomial in M. So what is known here is, so it's that the complexity of the determinantal complexity of the permanent has a very small lower bound so far, but even this is a very hard result, that you need at least an m squared over 2 matrix if you want to compute the permanent as the permanent equal to the determinant of a certain size. And the determinantal complexity of the permanent is actually less than or equal to exponential 2 to the m minus 1. And in fact, there is this very nice Reiser's formula, which is very explicit, and you can try to see why this is true. It's like an inclusion-exclusion type of exercise, which shows that the determinantal complexity of the permanent is at most m to the n times 2 to the n. So there's 2 to the m comes from all this, counting all this, going over all these sets. Okay, so this is the state of the art in terms of bounds, and basically we are trying to show that the determinantal complexity of the permanent is more closer to this upper bound than any of the lower bounds. So how can we try to approach this? And so here is when this geometric complexity theory comes in play, because these determinants and permanents, they have a lot of symmetries just by, as you can see from the description of this polynomial, so we can actually maybe try to use that somehow. So here are, again, the determinant and the permanent, and what are we trying to show is that the permanent cannot be written as a determinant with entries that are affine linear forms for any n of polynomial size. So when I said affine linear forms, there is also a constant term, so we are going to get rid of it by just normalizing. So we are going to make them of the same degree. So this is what's called the padded permanent also, which we can use any variable. Turns out that the same variable x11 is fine to the power of n minus m to equalize the degree. So we can just think of so we can get rid of the constant terms this way, and we can think of the entries in the determinant, in the matrix that's given as an input to the determinant, that they are now linear forms in our variables. Okay, so So where is the symmetry coming from? So first of all, of course, so the determinant, so if you change rows and columns and things like that, of course, the determinant changes just by sign, or it doesn't, and the permanent also stays the same. So how can we use all of these things? And the thing is to observe what's going on here. So if we have such a presentation, we can take all matrices, all possible matrices that we can plug in here. This is going to make us a space of polynomials. And so these matrices are not necessarily invertible, and they have to be n squared by n squared because we have n squared many variables here. So to remedy this, we can take the orbits of the invertible matrices acting here, so GLN squared, and take the closure. So this is going to capture everything we can get this way. And so if the permanent is actually in here, is equal to this, then it means that if we do the same procedure, just take the same orbital for the permanent here, this whole thing is going to be contained in the orbit closure of the other one. So this is how we capture this unknown generic presentation that we don't really understand. And now we can talk about these spaces. So what are these spaces? These are actually varieties. And we can look at the coordinate rings of these varieties in some degree D. So if the inclusion holds here, then the coordinate rings also have an equivariant map from one to the other. So we want to show that this is not happening for n equal to polynomially sized m. So that this coordinate ring does not have an equivariant map going into the coordinate ring for the orbit closure of the determinant. Okay, so this is some heavy setup here, so of course the question is, what are these coordinate rings and why is it better to look at them? This is a hard question, but so we can. So since there is an action of GLN squared, we can factor them into irreducible modules with some multiplicities. So here, these multiplicities for the permanent are going to be denoted by gamma. Again, these are the Weyl modules, GLN squared representations. And here are the ones for the determinant. So the multiplicities are delta. And we want to figure out when is an inclusion here possible, or an equivariant map possible. So if it happens that the multiplicity here is smaller than the multiplicity here, then this is not going to be possible. Then then we don't have this arrow. And in particular, if we actually show that this is happening for n greater than polynomial, for n bigger than any polynomial of m, then we are going to have that Vp is not equal to Vnp. Because then it will follow that the whole chain of reductions here that we had, that basically the determinantal complexity of the permanent is not that n. And if it also happens that the delta, so that lambda doesn't show up at all here, so this delta is 0, and the gamma is positive, then this is what's called an occurrence obstruction. So basically, if we find such a lambda for which these multiplicities satisfy these inequalities, we can say something about the complexity of the permanent versus determinant. And because these multiplicities are difficult, so they are worse than what I was talking about in the first talk, so about Chronica and platism, these are even less known. So we may want to restrict ourselves to to this delta equal to 0 and see if we can just find something that is 0 for the determinant and non-zero for the permanent. And that was one of the working conjectures of GCT, that there exist occurrence obstructions that for n greater than any polynomial in M. And unfortunately, this is false. So we cannot do this for n bigger than m to the 25th, and probably even less, but we didn't try to optimize that. So, okay, so from then, so what do we do then? So first, I'll tell you about how this type of question was answered, and then go back here. So here we ruled out occurrence obstructions, but we didn't rule out any obstruction, which is called multiplicity obstructions. And we'll go back there and see if we can still do anything about that. So just to recap from the first talk, so we had three main players: Littlewood-Richardson coefficients, Chronica coefficients, and platism coefficients, which are all multiplicities in various representation of the reducible representations in various of this tensor product or compositions. And of course, so we don't really know much about the Chronica and the platism coefficient. That was part of the punchline, but we still know something to work with them. And now these guys are going to show up now. So they're going to show up as upper bounds and very close ones in some sense. So the Chronica coefficient, the rectangular one, is going to be an upper bound for the multiplicity in the determinant. And the platism coefficient is going to be an upper bound for the multiplicity in this gamma. So unfortunately, we don't also have lower bounds because we want to figure out inequalities between these two things. But that's still not so bad, and we can still say something, at least for this negative result. So in particular, one of the preliminary conjectures before this, the occurrence obstruction, was that we can actually work with partitions lambda for which the Chronica is actually 0. So if the Chronica is 0, this automatically becomes 0. So all we need to do is figure out whether this gamma is strictly bigger than 0, and then we actually have a bound for the determinantal complexity of the permanent. And so this is the first thing that we actually disproved, and I will explain it now because for the other multiplicities it's a little bit more involved. So what we proved is that the Chronicas are basically positive for everything we would care about. These types of Chronica coefficients are all positive, and in particular, using this determinantal complexity notions and algebraic complexity theory, we can derive such an inequality between Chronica and platism coefficients, which is not clear a priori from representation theory, as far as we know. So, any questions before I move on? Okay. So how did we prove this if we don't know, if we don't have any combinatorial interpretation about for the Chronica coefficients? So here is really the statement. So if we have a partition lambda and then we do two rectangular partitions, so this should be n to the d and n to the d, so n and n d many times. So if the Chronica is 0, then gamma is also 0. But we actually okay. So what can we How can we prove this? First of all, we need to characterize what are the gammas that could possibly show up. And so here are two results that would be necessary. So one is that if the multiplicity, so if this gamma is bigger than 0, then lambda 1, the first part of the partition, is actually very long. So the lambda 2 and so on, from then on, there is most sum up to m times d. And the length of lambda is less than or equal to m squared. And this is because of the number of variables that show up in the polynomial. Then there is also a degree bound. So if we are already in this situation, and we do, so we actually, remember, we are looking for the Kronecker being 0, and the gamma, which is bounded above by this a, should also be should be bigger than 0. Then we actually need to have that the degree for the regular functions that we're looking for in the coordinate ring should be bigger than n over m. So we have some bounds for what partitions lambda can show up. And basically for all of those, we show that the Kronecker is positive. And except for some special cases, which we then do by hand. And how do we do that the Kronecker is positive if we don't know anything about the Kronecker? So we still know something. So the first part is to decompose our partition. So sorry, there should be lambda 2, lambda 3, and so on. So we decompose it into almost squares of various types and small partitions and single rows, single columns, and with two rectangles. And for each one of them, we will prove positivity. So basically, we know a bunch of things. We know that the Kronecker coefficient for 3 squares, the same size, of course, is strictly bigger than 0. So things that look like this, remember that we are missing the first row, but we can add this on top, is going to be positive. Then we can do various transpositions, still preserve the Kronecker coefficient. We can show that if lambda is close to a hook, so what is a hook? Is a partition that looks like this, and then we can do some other finitely many partitions over here. So things like this will always be positive. And the last part is that we can use this semi-group property, which actually comes from the from Schur-Weil duality and actions of general linear groups, to show that if we have two positive Kronecker coefficients, then we can construct another positive Kronecker coefficient by adding up these partitions. So basically, if we figure out that using this stuff, that these building blocks here for our partition are positive, then we can use this to compose our final partition and somehow deal with the rectangles so cut up the rectangles into various squares and smaller rectangles, and apply this inequality to actually get a positive Kronecker coefficient out of these building blocks. Okay, so let me show you in the opposite direction, how the geometric complexity theory and algebraic complexity theory can be used to derive such an inequality. So this is a different side of the matter. So let's take a partition rho and then take the other partition lambda, which is basically adding a first row to lambda and then adding the rest of lambda over there. So lambda is going to be something like this, and this partition here is going to be rho. So let's suppose that the Kronecker coefficient is smaller than the platism. So we argue by contradiction and take a smaller partition mu. So mu would be something like this over here, and this part would be kind of long, but still m should be big enough. And so the first thing to observe is that, so that we have this result if we take Vm to be the space of all polynomials in m-squared variables, so all polynomials of degree m in m-squared variables, which is what this really means, and we take the orbit closure, that we get basically everything. So that means that the multiplicity here is greater than or equal to the multiplicity of to the platism coefficient. Then we also have a stability result which tells us that the Kronecker coefficient stabilizes when n or d grows. So if we are just increasing our first row in the partition and increasing the sizes of the rectangles, this is going to have the same value at some point. And in fact, we know exactly when. So when n and m are greater than or equal to the size of rho. And now we can use we can use GCT to say that the multiplicity. So if so, the multiplicity here is, so this contains all. So if the multiplicity is bigger than this so it is bigger than this platism coefficient, and the platism coefficient we are assuming is bigger than the Kronecker coefficient. The Kronecker coefficient is also bigger than the multiplicity in the determinant, in the coordinate ring orbit closure of the determinant. So we have this inequality. So what does this mean? It means that this space over here is not contained in the orbit closure of the determinant because the multiplicity is bigger there for some partition. And in particular, what it means is that some polynomial here is not, it cannot be presented as a determinant of size n of some matrix with affine linear entries, which means that the determinantal complexity of the polynomial is bigger than n for some polynomial f in this space over here. And now basically we just follow the inequalities. So following this inequality, we get that the determinantal complexity of this polynomial should be bigger than n. Because of the stability, we can take n to go to infinity. So going over all this fixed degree and variables polynomials, we get larger and larger determinantal complexities. But this is not possible because the determinantal complexities of all these polynomials would be bounded by whatever, some binomial coefficient in this case. Yeah. And this is a contradiction. So we get this inequality in particular from all this framework. So back into algebraic combinatorics. Okay, so since occurrence obstructions don't work, can we say something about multiplicity obstructions? So here is our situation back. So what we were doing is we were comparing permanent versus determinant. So we can do several things. So first of all, we can replace this determinant by any polynomial we like, and the permanent by any polynomial we like and see if we can compare those. So basically ask the question of, can this polynomial be expressed as the other polynomial with some affine linear entries is plugged in. And if we want to show that it's not possible, then it's enough to actually show that there is some multiplicity lambda which satisfies these inequalities. So there is some lambda whose multiplicity satisfies these inequalities. So we can plug in here, instead of determinant, some other VP complete polynomial. It's not just the determinant. We can do matrix power, iterated matrix multiplication, and so on. Or we can try to search for actually multiplicity obstructions, which means that we can actually try to find some lambda for which the inequality actually holds, even if the two things are not zero. And what we could do here is take a toy problem. So power some polynomial. You can ask whether we can factor it into linear forms. So, okay, that's probably easy. This is easy using any other methods you want, but we can demonstrate how it works in terms of the GCT perspective. So, what is the product of linear forms? Is actually the this is the space of all products of linear forms, and we take all the, so in this case, so this is actually closed already, and we can take the sum of the power sums and take this orbit closure. So this is going to be our analogs of the determinant orbit closure and the permanent orbit closure that we were doing, and we can compute them with the GCT paradigm. So again, we can try to find some multiplicity which shows up in one, and with smaller we can try to find some lambda which shows up in one with smaller multiplicity as opposed to the other. And what it turns out is that there are no occurrence obstructions here. So basically, if the lambdas show up in both at the same time, but then we can actually find the multiplicity obstruction, so an actual lambda for which this inequality holds. And so, in particular, we cannot express the power sum polynomial for k equal to n plus 1 in terms of linear forms. So what the ingredients were here is that, so first thing is we know what the multiplicity in here is, and this is something we needed for the multiplicity no occurrence obstruction result, is that this is just the platism coefficient that I had mentioned in the first part. Then we have some inequality for the Chow ring here, that this is less than or equal to the platism coefficient, but reversed. So notice that there is a d of n, and here there is nd. And then we can try to find some particular values for which the corresponding inequality holds, which we did. So we actually found that they differ by 1 for this particular partitions lambda, and we found a multiplicity obstruction. So it is, in theory, it is possible to still find multiplicity obstructions. Now the question is how. So if we want to distinguish the complexity classes, and the question is how. So I have a few more minutes. Maybe I can tell you what one could possibly try to do. And one can try to find asymptotics for these multiplicities that show up. So we don't have any combinatorial interpretation, no closed formulas, nothing, but we can actually look for asymptotics, and this is maybe going to reference a little bit So has to do with Amal's talk, for example, because it says about asymptotics of various structures that we already saw yesterday. So here are these lozenge tilings or plane partitions, and they are actually, so these plane partitions are counting, in some sense, semi-standard Young tableau. We can think of it this way, and we can do asymptotic algebraic combinatorics is very closely related to this type of questions as well. And then there is the asymptotic representation theory. So this some of you may recognize this as the Vershik-Kerov-Logan shape limit shape for the Plancherel measure for a partition. So these questions are relevant in these areas, but they are also relevant to what I just talked about in geometric complexity theory, because we need some ways to estimate how large these Chronicas and platisms are, even if we cannot compute them exactly. So, what kind of things do we know already? And basically everything else is going to be an open problem from then on. So for example, we can look at what's the range of values. So what's the maximal Kronecker coefficient, or the maximal Littlewood-Richardson, and so on. And so this is a result of Stanley. The Kroneckers are really big. There's like square root of n factorial, and factorial is the order of the group, right, of the symmetric group. Littlewood-Richardson coefficients are quite a bit smaller. But we don't know exactly when these maxima are achieved, but we can say something. So we can say that, for example, the Kronecker is maximal. If the Kronecker's gotta be maximal, then all these three partitions should look like this. So this is a rotated picture of the Young diagram, as if you can see the fine detail. So this is the Vershik-Kerov limit shape. So there, they should be somewhere near there if we're looking for a maximal Kronecker coefficient. But we don't know, we cannot say that for all three, if we have three partitions and they are all somewhere near this shape, we cannot say anything about that particular Kronecker coefficient. So this is an existence statement. So the other thing, we can bound the Littlewood-Richardson coefficients a little bit better for if we are fixing the partition sizes inside. And again, so there are some existence statements that this, if we are going to look for a large Littlewood-Richardson coefficient or a maximal, then we are going to need some maximal shaped partitions, so they should be close to this Vershik-Kerov-Logan shape, but and various other results. But again, so for any particular triple of partitions, we cannot really say how large it's going to be for any particular family. And there is another side of the story, which came from actually random matrix theory, that one can, because the Schur functions that I mentioned in the previous talk, they are related to the to random matrix integrals. So then one can actually find some upper bounds for using these Schur functions, and the fact that these are coefficients in the Schur function presentation, that there are, one can express this in terms of random matrix integrals and say something about that. But again, for any particular family of coefficients, we don't have explicit answers. So what else we can do? We can try to see what the bounds are if we have a smaller number of rows, so we are not stretched equally in both directions. So then the Kronecker coefficients becomes bounded by so it decreases significantly. But again, we don't really have any lower bounds. And how this works, can maybe show you Right, well, there is no time. So the proof, the proof goes through this symmetric function identities that we can use when the Kronecker coefficients show up. And they can be bounded by this T, and T is counting three-dimensional contingency tables. So this is beyond algebraic combinatorics. This is a very general object, very in statistics used and so on. So this is bounded by contingency tables, and we can try to figure out what this is asymptotically using for some values of lambda, mu, and nu, using Barvinek's methods, and to estimate this. So the other thing one can do is if we try to fix the diagonal of the partition. So basically, this is the largest square we can plug into this partition. So this is the Durfee size, the lambda. And if we actually have this bounded by some integer k, which is fixed, and then n goes to infinity, then we can say that the Kronecker is at most grows at most polynomially in terms of this parameter here. And in fact, we can also say that there is going to be some Kronecker coefficient which is at least polynomially large, but again, we cannot say which one. For which partitions this is going to be maximized. And the last thing the last thing is very, very special. It concerns the Kronecker coefficients when we have two rectangles, which was actually in the GCT setting, and just a two-row partition. It turns out that this is equal to the difference of consecutive partition numbers, which are so counting partitions inside a rectangle with given size. So the two consecutive things. So it turns out the Kronecker is equal to this difference, and it's already interesting if to see if combinatorially if this difference is positive. And using tilted geometric random variables, we could actually estimate this very tightly everywhere except right in the middle, and to figure out what the Kronecker coefficient would be in this particular case. But this is, of course, thanks to this particular, and I wouldn't even say this is a combinatorial interpretation or immediately, because we don't know that this quantity is positive a priori, just from this. And yeah, so this is our Kronecker coefficient in this particular case, and we don't really have any other exact asymptotic results for any other families of partitions. So thank you very much. Yeah.
So this is about your previous talk. So you were doing things that are not computable easily in some counterexamples. But you had a very nice formula for the sum of the entries in a character table in a certain column.
Yeah.
And is what you have shown that there's no real combinatorial interpretation for that sum, or?
So for each of the entries in the sum. So the total sum is what it is, right? So it's a product formula, but for each of these entries, we don't have, yeah. Yeah, so okay, I should say for some of them we don't have, because some characters, of course, are easy. We know we can do them, yeah. So, but there are certainly families of lambda and alpha for which we cannot say what this thing is. Yeah.
Is there an explanation of why the partitions that look like the Berkshire-Karoff-Logan limit shape maximize the Kronecker coefficients? They should be the highest dimensional.
Yeah, exactly. So
how do you get from there?
Yeah, so basically there are some very simple identities that give you bounds for. So we can write some sums and some identities. So first of all, the Kronecker coefficient should always be less than or equal to this dimension. But also that if you're, so then you can also show that the maximal Kronecker coefficient, because there is certain sum involving them, it's going to be on the order of square root of n factorial, which means that if the maximal Kronecker coefficient is on that order, then all these partitions will have big dimensions. So it is from this point of this type of argument. But again, I can show you the sums later that how exactly it works.
Okay, so then let's thank the speaker again. Maybe try to restart in 10 minutes.